of Oklahoma and received his PhD. And later on, he worked as a postdoctoral student at the University of Minnesota. Right now, he's visiting us. He has an impressive list of 40 publications, on 10 of which he is the primary author. So, John, welcome.
Thank you so much, Dr. Benitez. And I want to thank you all for coming here to my presentation. And thank you. There are two parts in my presentation today. In the first part, I'm going to show you two projects I did in the past few years. And the second part, I'm going to show you the research work I'm going to do in the future. Okay. So here, the first part is the research work I did. Two projects. The first project is about the reactions of triphenyl antimony sulfide with copper-1 complex. This is my postdoc work. Second project is about the synthesis and characterization of mixed valence copper complex and copper sulfide substance. And this is my PhD work. Alright, so before I show you the results of my research work, I want to briefly introduce the background of these two projects. Here, this picture is about the greenhouse effect. Okay. On the left side is a natural greenhouse effect. We need that because it can keep the earth warm. And the right side is the enhanced greenhouse effect. It's caused by the greenhouse gases. When we talk about the greenhouse gases, most people immediately think, oh, carbon dioxide. Actually, there are several different greenhouse gases. And among these gases, carbon dioxide, methane, and nitrous oxide are the three most important greenhouse gases. And here, this table tells you some very important information about these three greenhouse gases. Carbon dioxide, methane, nitrous oxide. The concentration of methane is the highest one. The carbon dioxide and nitrous oxide have similar concentration. But take a look at the lifetime and radiative efficiency of nitrous oxide right here. The lifetime of nitrous oxide is 114 years, which is much longer than both carbon dioxide and methane. The radiative efficiency of nitrous oxide is also much higher than the other two greenhouse gases. So this table shows us that nitrous oxide has a very big impact on the greenhouse effect. And every year, human activity generates about 7 million tons of nitrous oxide. And agriculture activities contribute about 60%. Asset industry is about 20%. And fossil fuel combustion is about 14%. It's kind of hard for people to control the emission of nitrous oxide from agriculture activities because all of these activities are in an open field, open space. It's kind of hard. But certainly we can do something to control the nitrous oxide emission from asset industry and fossil fuel combustion. The problem is how. So the scientists are trying very hard to develop a new catalyst to reduce the nitrous oxide. And it's a very exciting research area. And in nature, there is an enzyme, which is called the nitrous oxide reductase. And here, people found that this enzyme can reduce nitrous oxide very efficiently. And here, this is the equation. The two nitrogen atoms in nitrous oxide get 2 electrons to generate nitrogen. And water binds with 2 protons to generate, the oxygen binds with 2 protons to generate water. So, people are very interested in this function of this enzyme. And in the year 2000, the biochemists solved the crystal structure of this enzyme, and they found there are 2 metal sites in this enzyme. Here is 2 sites here, highlighted then by the green colors. Let's take a look at the metal sites. Here, the first metal site is a copper A site. It's an electron transfer standard. Remember, in order to reduce nitrous oxide, you need to give 2 electrons to the nitrogen atoms. And here, this transfer standard provide 2 electrons to the catalytic center, which is copper Z side, then reduce the nitrous oxide. Okay? It's a mixed valence copper dimer, okay? And there is a weak interaction between the two copper centers. And more importantly, we got this structure of the catalytic side. It's called copper Z side. You can see there are 4 copper centers. And among these 4 copper centers, there is a mu4 sulfide bridging ligand. This is a very unique structure, and people have never seen this kind of structure before. And the whole structure, the whole cluster is supported by 7 histidine groups. And according to the biochemistry biochemistry research and computational study, people believe that this copper A is the binding site of the nitrous oxide molecule. Okay? Nitrous oxide will be a bridging ligand between the 2 copper centers, and then the next step would be the cleavage of the NO double. And remember, before the binding of nitrous oxide molecule, the whole cluster is fully reduced. So that means all 4 copper, the 4 copper centers are copper 1. And the fully reduced copper Z side can give 2 electrons to the nitrous oxide. And then the whole cluster will be 3 copper 1 and 1 copper 2 plus. So there is some redox and oxidation process during the cleavage of NO bond. So after we got this now we got this structure of this catalytic side, what should we do? For bioinorganic chemistry people like us, we try to learn something from nature. We want to develop the synthetic and functional model of this copper Z side, and we hope that the model can have the same catalytic function toward nitrous oxide. That is our research goal. So in our project, we're going to use the neutral endothermal ligands to mimic the histidine groups in the copper Z side. And then we will use this ligand to construct a structure model of the copper Z side. And after we get this complex, we will investigate the nitrous oxide reactivity. Alright, so here are the ligand and sulfur ligand system and sulfur source we use in this project. We use the 2 ligands, the trimethyl TSM ligand and the TMCHD ligand. Both of them are neutral end-donor ligand. And here are the copper 1 complexes we used in our project. You can see that both ligands can support copper 1 center very well. This is the sulfur source we use, triphenyl antimony sulfide. From previous research, people found that this sulfur source is a very good sulfur delivery reagent. For instance, in the year 2008, Tom from Harvard University reported a reaction. When you use this constant complex react with this triphenyl antimony sulfide, this constant sulfide complex with very interesting structure and spectroscopy conventions. Okay. So in our project, we would like to use this sulfur source and react with our copper 1 complex to construct the copper sulfur complexes. Alright, so let's see the first reaction we tried. When we use triphenyl antimony sulfide react with this copper 1 complex supported by TACN ligand, we observed the formation of this 1-to-1 duct. There is no redox or oxidation process. The sulfur antimony double bond is here, and copper center is here, copper 1. And we saw the crystal structure of this compound, and here you can see the copper sulfur antimony form a bond which is about 120. So, and one interesting thing about this compound is at room temperature it can slowly decompose to this dicopper 2 disulfide species. And it's very interesting because we observed the cleavage of this sulfur antimony double bond. The copper gets oxidized from copper 1 to copper 2. And antimony before